Welcome back, everyone. In this video, we will be covering the final part of Lecture 13. The topic is American options in the multi-period binomial model. Okay, let's get started. Every option we have priced so far has been a European option. This means that the option could only be exercised at date capital T, i.e. the maturity date. In contrast to European options, though, American options can be exercised early at dates prior to the maturity date capital T. What we want to ask in this final video is how does this early exercise feature affect the pricing calculations for American options? To answer this question, let's start by thinking about how we price European options in the multi-period binomial model. It turns out that European options interact well with this type of model because they can be priced in what is called one-shot. One-shot pricing means that we only need to consider the events that occur at date capital T, and effectively we can ignore everything that comes before the terminal or maturity date. For example, let's look at the European put price formula. The European put price formula, P0, is given by the following equation. First, we know it comes from the FTAP. It's equal to the expected discounted payout, under the risk neutral measure, which we learned earlier in this lecture is equal to this long formula, e to the negative RT times the sum over the terminal states, n choose I, QU to the I, 1 minus QU to the n minus I, times the put payout, K minus ST of I. This was just equal to nothing more than e to the negative R times T, sum over the states, the risk neutral probability of state I, times the put option payout in state I. Okay. Note that the European put price formula only depends on quantities that are known at time capital T. It depends on time capital T payoffs. It depends on time capital T maturity. And it depends on nothing prior to this date. Okay. This means that the model can be priced, is being priced in one shot. We just basically simulate whatever happens at this final terminal state, and that's all we really need to know. Okay. In contrast to the European options, okay, American options payoffs are actually going to depend on events prior to date T, and this is because they depend on early exercise conditions at the intermediate states. This dependency on prior date payoffs means that American options cannot be priced in one clean, easy, one-shot formula like we have here. Instead, they need to be priced using an algorithm called backwards induction, which is going to prevent us from using a nice clean formula. Backwards induction is going to work by essentially recursively pricing the American option at each stage in the tree. So you price the option at every node within the tree, okay? And in each state or in each node, you compare, okay, the model prices to the early exercise value. If the European model price is below the early exercise value or the option has negative time value, then the option will be exercised early. And this early exercise decision will flow backwards throughout the tree and affect all prior pricing. Okay? This we will not learn how to do in particular in this class. It's easily referenced in your textbook. It's just messy and it takes a lot more time than pricing European options. Okay, but the reason we care about this is because more oftentimes in reality, we're dealing with American options than European options. And what this nuance means is that the lack of one-shot pricing means that the computation time is going to be much larger for American options. Okay, you're not going to be able to have a quick and easy formula like we do with the European put price. Instead, you're going to have to work iteratively backwards behind the tree, which is going to drastically increase the number of computations you need to solve the model. For example, suppose you have an end period tree. If you want to price a European put option, all you have to do is compute payoffs and probabilities in a total of n+1 states, terminal states. However, to price an American put option, you would need to perform over 2 to the n computations. As n becomes large, the difference in the computation times becomes enormous. For example, take 2 to the 100th power and compare it to n+1 equal to 101. The number of computations needed to solve this American option model is going to be enormous, which is why we skip this mostly in this class because it is too time consuming. Okay, so let's conclude. Lecture 13 was all about the multi-period binomial model. We started by thinking of a two-period model and then generalizing to n periods. We derived a formula to price any derivative in the two-period model. It was again just the derivative price, x0 was equal to the risk-neutral discounted payoff. Okay? And this expected payoff, okay, this risk-neutral expected discounted payoff, the expectation portion in a two-period model was simply equal to the probability weighted average over the states of the payoffs. Okay, so it was just the states, QUU times XUU, and then there was state UD, you multiplied the probability by the payoff, and so forth all the way throughout the tree. This formed this expectation. Okay. We then generalized this pricing model to n periods. And in particular, what we did was we dealt with call and put options because it allowed us to solve for quick and easy formulas based on the stock prices. Okay, you could still price any general derivative in this model. It's just easier for instructional purposes to work with calls and puts. We saw that as the end period tree grew bigger, the number of computations we have grows, but it only grows linearly in this case. And again, it's just the same exact thing as before, except now we have an explicit structure on the probabilities. Instead of just being QUU, we know that's exactly equal to this n choose I, QU to the I, 1 minus QU to the n minus I, which we also denote as Q of I. Okay. Essentially, everything just boils down to the FTAP again. The FTAP just states that the price of a derivative is its discount expected payoff under the risk-neutral probability measure. This forms the basis of all this pricing. Whether we're working in the two-period or n-period tree just affects how this expectation looks. How many terms are in it? How many payoffs do we need to wait? Okay, a quick note on hedging before we go. Okay, so a quick note is that when we dealt with hedging in the one period binomial model, we had a static hedge. We came up with a delta and a beta, and then we priced by replication using this static hedge. We then shifted to risk neutral probability pricing, okay, which we've done throughout most of this lecture on the multi-period tree. We could have equivalently priced using replication all throughout this lecture. It just would have taken a lot more time. It uses the same exact logic, and it's going to take more computations because what's going to happen is that a static hedge is no longer going to work in the multi-period tree. Instead, you're going to have to rebalance this hedge dynamically, and this can make computations get really messy, really fast, and so mostly we just avoid this, stick to risk-neutral pricing so we can do one-shot formulas and make it quick and easy. So that's it for lecture 13. I'll see you guys in the next video where we're going to move the model to continuous time and talk about Black-Scholes.